Once we know how to add matrices and once we know how to multiply matrices, we need laws to combine the two operations. We'll start with first rules for matrix addition. So for matrix addition, we have the commutative law. A plus B equals B plus A. So this is called the commutative law. This law, if you think about it, is pretty natural. It just means that it doesn't matter, the order in which we add two matrices is not important. And why that is the case is because matrix addition is defined term by term, and ultimately what we are adding is two numbers, and we do have commutativity in terms of number addition. Now, what if we multiply the sum by some constant c? Well, we could first carry out the addition and then multiply by c, or we could first multiply the matrix A and the matrix B by that constant c and add the result. This is called the distributive law. So this constant scalar multiplication is being distributed over the sum. Finally, we have the associative law. So addition is a binary operation. It tells us how to add two things. But what happens if we want to add three things? Well, we can't add three things all at once, so we have to decide which two matrices to add first. Well, what the associative law tells us is that the order in which we add two matrices is not important. We could add first the matrices B plus C and then add that sum to A, or we could first choose to add A plus B and then add that result to C. The answer would be the same. All of these laws follow from the same laws for addition of two numbers. And because matrix addition is defined term by term, we're adding the components of the matrices one at a time. The laws for addition get pulled into the matrix laws for addition. So addition of numbers gets translated into addition of matrices with the same laws. Multiplication is not exactly the same. So for multiplication, the first rule does not work. A times B is not always B times A. So the commutative law usually fails. So sometimes you can multiply two matrices and the order will not matter, but more often than not, the order matters a lot. We'll look at examples to see why this would not be the case. But even if you just think about how we define multiplication of two matrices, in order for two matrices to multiply, their sizes have to be appropriate. Well, if you have, I'll just quickly jot this down. If your matrix A is of size m by n, then you know that your matrix B must be of size n by k. Well, when you multiply the two together, the product must be of size m by k. Well, what happens if I write n by k multiplying m by n? This can only happen if k and m are equal. But to carry out A times B, it is not necessary that m and k be equal. So you see, even from the sizes, it is not always possible to carry out the multiplication. So this is possible only if k equals m. And if k equals m, or rather, if the two matrices, so if the one, it would just say that you have a matrix M by N and a matrix N by M. Well, if M and N are different, then the two matrices, although square, would be different. So one could be 2 by 2 and the other one could be 3 by 3. But even in the case of square matrices where both multiplications are possible, you don't have a guarantee that the products will actually be the same. So I'll remove what I have here, just because I want to write something else, and we'll come back to that discussion again. The next law is the distributive law from the left. So if I want to combine addition and multiplication, from the first law, we see that it does matter on which side a matrix multiplies, whether it multiplies on the left or it multiplies on the right. So we have to have rules for multiplication or distribution of multiplication onto summation from the left and from the right. So here you have AB plus AC. Distribution, you don't see anything sort of out of the ordinary. So this is the distributive law from the left, because the matrix A is multiplying on the left-hand side of the sum. And you have the same law for multiplication on the right. So you could first add A plus B and then multiply by C, or you could carry out the products AC and then add that to the product BC. So this is distributive law from the right. And finally, we have the associative law for multiplication. So just like addition, multiplication is also a binary operation, which means it happens between two matrices. Well, when we have 3, we have to we can carry out the multiplication, but it has to be done 2 at a time. So what the associative law says is that you could first choose to multiply B and C, and then multiply that product by A, or you could multiply AB, find that matrix, and multiply that result by C, and you would get the same answer. So this is what's called the associative law for multiplication, which essentially means that parentheses are not needed. Now, something which is really important over here to understand. Because matrix multiplication is not commutative, because A times B is not B times A most of the time, this is very important. If A multiplies B and C on the left, then it has to continue to multiply B and C on the left. So if it multiplies the sum B plus C on the left, then A multiplies B on the left, A multiplies C on the left. You cannot change the order over here. You cannot write B times A, because that would be a completely different matrix, and sometimes it might not even be defined. So this is something that we have to be careful about. Let's see an example of when the commutative law for multiplication fails. So here's a simple example. Let's say the matrix A is 0, 0, 1, 0, and the matrix B is 0, 1, 0, 0. Now, both of these matrices are 2 by 2. So it is possible to compute both A times B and B times A. The result in either case would be 2 by 2. Let's see what is A times B. So this is 0, 1, 0, 0, multiplied by 0, 0, 1, 0. You can carry out the multiplication however you like. I'm going to do dot products. So I'll use this vector times this vector. That gives me a 0 here. Then I will compute this row times this column. The dot product is 0 times 1 plus 0 times 0, so that's another 0. Then I'm going to compute this row by this column vector. Well, you have 1, 0 times 0, 0, so that gives you a 0. And finally, I have this row multiplied by this column, so with dot products. So that's 1 times 1 plus 0 times 0, that's simply 1. So we got that matrix. Now what about B times A? B times A is 0, 0, 1, 0, multiplied by 0, 1, 0, 0. And similarly, we do this row times this column as a dot product. That gives us a 1. Then when we take the first row from B and the second column from A, we just get 0. Then second row of B, first column of A, that's 0, and then we get another 0. You see that A times B is not equal to B times A, even though both are defined. When I assign the problems for you to consider, you can try out the other laws to see why they work. Thank you.